Hi, I'm Rick Becker from AT&T Bell Laboratories. I'll be showing you a high-interaction graphical technique known as brushing a scatterplot matrix. The basic tool for this technique is a high-resolution bitmap display terminal, which includes a powerful microprocessor and a mouse for interaction. Our particular terminal here is an AT&T teletype Model 5620. We will use 3 sets of data to illustrate basic brushing operations. Our primary purpose is to show how brushing works, so we won't spend much time interpreting the data. This is a scatterplot matrix display of Fisher's iris data. These are measurements of sepal length, sepal width, petal length, and petal width for 150 iris flowers, 50 measurements from each of 3 species. If you look straight across a single row, you see, for example, sepal length on the vertical axis of all 3 plots in the first row, petal width on the horizontal axis of all 3 plots in the last column. The center diagonal is used for the labeling and also contains, at the corners, minimum and maximum values for the particular variable. So the minimum sepal width value is 2.12, maximum 4.31. The plot with the highlighted border is called the current plot. The rectangle in this plot is called the brush. As points move into the brush, they are highlighted. And they are also highlighted on the other scatter plots within the scatterplot matrix. If I hold down button 1 as I move the brush through the points, I can paint in a cluster. So, for example, I can color in this upper left cluster and notice that on the plot below, it corresponds to a very tight cluster of points down here, which have short petals. Unlike a regular paintbrush, I can also unpaint things by pressing button 2. So I can go back and erase the points that I had just colored in. I can use button 3 on the mouse to pop up a menu, which will allow me to change from highlighting to deleting points. Now, any points inside the brush are deleted momentarily from the current scatter plot and from the other scatter plots. So if I use the delete with button 1 held down, I can make the deletion more permanent. Of course, if I change my mind, button 2 once again lets me undo the same process. Let's get rid of our top cluster. But this time, let's rescale the data so that that cluster is gone forever. Again, using the pop-up menu, I can pick Rescale, and the scatter plots are redrawn with those points omitted. The four-dimensional iris measurements gave us an opportunity to see how brushing works on clustered data. The three-dimensional abrasion loss data lets us show an important brush technique, conditioning on a variable. With the rubber abrasion loss data, our primary interest is in predicting abrasion loss as a function of tensile strength and hardness. So we can look at the scatter plot in the lower left-hand corner and see that abrasion loss seems to be fairly negatively correlated with hardness. It's much harder to see what relationship we have between tensile strength and abrasion loss. However, let me momentarily pick a brush which is quite different shape than before. I'm going to make it long and narrow. And I'm going to sweep the brush from left to right across the hardness plot. What I want you to direct your attention to is the plot down here showing tensile strength on the x-axis and abrasion loss on the y-axis. Notice the pattern formed by the highlighted points as I move from left to right. Now, if we zoom in on this scatter plot, we can look in more detail at that same picture. I think now you'll be able to see that there appears to be some curvature in the relationship between tensile strength and abrasion loss once we've conditioned for a certain level of hardness. Discovering this kind of curvature by means of other kinds of displays is quite difficult, whereas using the scatterplot matrix techniques, it popped right out at us. We were able to show the curved tensile strength abrasion loss relationship because we could interactively condition on a third variable, hardness. Our next example shows how we can deal with larger sets of data, discrete variables, and observation names. Our next set of data involves measurements of body weight and brain weight on 164 animals. We've used the logarithms of the body and brain weights because of the large variability of those measurements. Here we have log body weight, log brain weight, and family, a categorical variable which takes on values showing birds, fishes, primates, non-primate mammals, and dinosaurs. The first thing we can do is to make a very small brush, get into label mode, and look at the names of some of our outlying animals. Here, for example, we have a little brown bat, very small. Here is a perch, a moray eel. If we move to large animals, we have a diplodocus, a brachiosaurus. If we look towards the higher brain weights, we find a blue whale, African elephant, Asian elephant, and porpoise. Of course, it might be interesting to find man on this plot. We can use locate mode in order to do that. with locate mode, we have a menu that we can scroll up until we find man. We can confirm this using our labels. Here's man right next to the porpoise. By now, you've probably formed a general opinion of what's going on in this scatter plot. In general, the body weight and brain weight seems to follow a fairly straight line, and you might assume that the animals on the low side of this line are ones of lower intelligence. The ones on the high side have somewhat larger intelligence. If we now try to look at the different animals by family, we can see some tighter relationships. We'll form a large, narrow brush and highlight certain families. For example, the highlighted points are the non-primate mammals. Here are the primates, the fish, and the birds. Of course, there's a lot of clutter in the scatter plot, and one way of cleaning that up is to use shadow mode. In shadow mode, only the points which are inside my brush are shown on the other scatter plots. So here, for example, are the fish, the birds, the primates, the non-primate mammals, and the dinosaurs. We could use the non-primate mammals as a kind of normal scale and see which animals seem to be smarter or less smart. For example, our primates, flashing on and off, tend to be above the line of the rest of the mammals, indicating somewhat higher intelligence. The fish are definitely below the line. The birds are on the low end as far as weight is concerned, but seem to fall fairly much among the rest of the mammals. And the dinosaurs, well, the dinosaurs are big, dumb, and dead. Brushing a scatterplot matrix is an important new tool for data analysis. It gives the user a natural way to control the power of a modern computer and graphics display.